normal search problems, which we looked at so far, we haven't had an opponent. We've just been trying to solve a puzzle. But when we've got games between one agent and another, you've got an opponent. And you can, to a certain extent, predict what they're going to do, but you don't really know. So our solution is going to be a strategy which will specify a move for every possible play that the opponent might make. In other words, no matter what they do, we'll figure out something to do that's the optimal to do. Now, in many games there are time limits, and if that's the case, we may not be able to find the goal, so we're going to have to approximate and use heuristics to do that. The use of game playing in AI has a long and distinguished background, and it goes all the way back to Charles Babbage in the mid-1840s, who thought about having a computer consider possible lines of play. And indeed, many of the results come from some of the absolute original thinkers in computer science. So for instance, the notion of an algorithm of perfect play is due to Zermelo in 1912, but also to von Neumann in 1944, who developed the modern architecture for computers. Similarly, the notion of a finite horizon, in other words, we can only be able to see so far into the game because we have limited resources of computing in order to be able to figure out the best move, and thus we need an approximate evaluation, is due to Zeus in 1945, but also Wiener in 1948, and also Shannon in 1950. And Shannon, you may recall, has been immortalized as Shannon codes. The first program for chess was written by none other than Alan Turing himself in 1951. And machine learning, which we're not really addressing in this class, but Dr. Fuentes is addressing in his class, was done as early as 1952 to 1957 to improve evaluation accuracy. And McCarthy, another one of the absolute classic founders of computer science, developed the notion of pruning the search tree to avoid expanding areas in the tree that we're never going to get to realistically, and so that we can go deeper into the tree, look farther into the future, as it were. So lots of serious thinkers in games, even though they're fun. So let's think for a moment about the kinds of games that we might play. And we can classify them across two dimensions. The first dimension is whether or not the game is deterministic or has an element of chance. The second dimension is whether the players have perfect information or imperfect information. So deterministic games are ones like checkers or chess or Othello, where there's no element of chance. The players don't draw cards or roll dice. In contrast, games of chance include games like Monopoly or backgammon, and card games. So that's deterministic versus chance. Seems pretty clear, right? In terms of perfect information, the issue is whether or not the players have access to all the information about the game. So in a board game like chess or checkers or backgammon or Monopoly, both players can see the entire game and they know everything there is to know about it. But in a game like Battleships or Bridge or especially poker, let's say, the players have imperfect information. They know about their own battleships, their own cards, but the whole point of the game is that they don't know about uh, the positions of the battleships or the cards of the other players. So those are the kinds of games, and we're going to start out with a simple deterministic game with perfect information, and that's tic-tac-toe. And so we'll be developing a tree to show the possible moves of the players, and in this case it'll be a two-player deterministic game where the players take alternate turns. So let's start out with the first player, and that's going to be the player that we in our computer are going to try to help win. And we're going to call this player Max because we want to maximize the result of the play. And you'll see how that works. So for tic-tac-toe, Max has the possibility of making any one of 9 moves by putting an X in any one of those squares. And when Max does so, the other player, whom we're calling Min, who's got the O's in tic-tac-toe, is faced with any one of these 9 possible choices by Max. So what we do is expand out what Min's possible plays would be for each of these plays by Max. And I'm only going to do that for the first possibility on the left there, because otherwise we'd be here all day and all evening, and this will be plenty to get the idea. So anyway, let's expand the first branch there, and these are the kinds of moves that Min might make, and thus represent the situation that Max faces after Min's first move. Now, if Max does play in the upper left-hand corner and Min does play in the upper middle square, then Max has a set of plays that we can lay out as new branches of the tree. So there are 7 possible moves because there's 7 blank squares left, and we can basically lay all those out. And those 7 possible states are what Min will be facing when Min has to take the next move. So let's say we have this situation XOX here, and what moves could Min take? Well, eventually we'll get down to terminal states where no more moves can be made. And so, for instance, one terminal state, which is in the direct line from XOX here, is that Min is going to win. The next one over here is a stalemate in which nobody wins. The next one over, for example, is one in which Max wins. And we can assign values to each of these outcomes based on the notion that we want Max to win. So the utility function for these outcomes is we'll assign -1 to the case where Max loses, a 0 to the stalemate, and a +1 to the case where Max wins. And that's how we draw a tree that represents the possible set of states for the game. Now that we know how to create the state space to describe play in a 2-person game, let's think about what strategy we should take to get the best chance of winning. Well, in the case of a deterministic perfect information game, like chess or tic-tac-toe for that matter, the perfect play can be achieved through a strategy called minimax. Now, the idea here is that we assume that our opponent, Min, will always take the move that's most in Min's favor. That is, Min will try to minimize the utility function for max. In other words, we are going to try to get the best achievable playoff we can get against the best play that Min can make. And that utility function is called the minimax value. And we'll always try to choose for max the position with the highest minimax value. So for example, in a game that where the players alternate moves, so it's called two-ply, here's how it would work. So let's say that Max, whose moves are represented by an upward-facing triangle, let's say that Max has three possible moves, A1, A2, and A3. Let's take a look and see what happens when on the A1 branch. Min, whose positions are represented by the upside-down triangle, turns out to have three possible moves, A11, A12, and A13. And if we evaluate the utility function for those moves, it turns out, in this case, that the nodes have, the states have values of 3, 12, and 8 respectively. Now, as much as we want Min to choose to make the move to A12 where the value is 12, Min is never going to do that because it's not in Min's interest. Rather, Min is going to choose to make the move towards the state with the lowest utility value, 3. Therefore, we know that the maximum value that this node could have for max is going to be 3 because Min is always going to choose the 3 node, not the 12 or 8 nodes. The same kind of logic applies if Max takes move A2. So if Min is here and Min's choices are states with values of 2, 4, and 6, Min will always choose the value of 2. That means that the maximum value to max of this at this point is going to be 2 because Min, if Min is rational, will not choose the 4 or the 6. The same reasoning applies if Min moves, if Max takes the A3 move. At this point, Min's choices are nodes with state utility values of 14, 5, and 2, and by the same reasoning, Min will choose the node with 2. That means that when Max is considering what move to take, Max faces 3 nodes, one with a utility value of 2, another with a utility value of 2, another utility with a utility value of 3. Therefore, Max picks this one because it's the greatest of all the minima that Min will choose, and that's why it's called minimax. So what are the properties of minimax? Well, in terms of completeness, yes, it is complete if the tree is finite. And in games that you might think are not finite, like chess, well, they have rules like for multiple repeated moves that lead to stalemate. So in effect, it is finite. Optimal, yes, against an optimal opponent. In other words, minimax assumes that Min will always take the move most favorable to Min. If Min doesn't do that, well, then it's hard to predict. In terms of time complexity, it's order of the branching factor to the maximum depth. And in terms of space complexity, assuming we do depth first search, it's O of B times M, which is terrific. Now, it's not necessarily feasible to do a complete tree, explore the complete tree. For example, chess has a branching factor of roughly 35 and a maximum depth of roughly 100 moves for reasonable games. And so O of 35 to the 100 is a very, very large number. So an exact solution is completely infeasible. So that's how minimax works. And in the next chunk of the lecture, we're going to see if there's some way to cut down on that state space. Maybe we can go deeper by avoiding to having to explore every possible path. I mentioned that it would be advantageous not to have to explore the entire search tree if we could avoid it. So it turns out there is a technique for doing that for minimax, and it's called alpha-beta pruning. And here's how it works. So in this example, we're looking at the same search tree we looked at for the minimax example. And if max takes this first branch here, we're looking depth first, we know that the value of this node has to be 3 because if min is going to choose between 3, 12, and 8, min will always choose 3. So we know that this value is going to be 3. But that also tells us something about this node. And what that tells us is that the value of this node has to be at least 3. Why? Because it can be 3 because max could choose to go here, so we've got at least 3. And there might be other values out here on the unexplored paths that could be greater. So the value of this node for max is greater than or equal to 3. Now let's expand in our depth first search the next possible move for max, sorry. So when min is here, and we've expanded the very first node depth first wise, and we get a 2, we know at this point that the value of this node has to be less than or equal to 2. Why is that? Well, because if the values represented here by the x's were greater than 2, min would never choose them. If they were less than 2, min would choose them, and then the value of this node for min would still be less than or equal to 2. So given we know the value of this first branch of this node is 2, we know that the value for min is going to be less than or equal to 2. Now stop and think for a moment. If max has a choice between a node whose value is 3 and a node whose value is known to be less than or equal to 2, max will always choose this node. There is, even if the values here where the x's are turn out to be 45 and 128, min is never going to choose them because min will choose 2. And if they're less than 2, min will choose that, and this is going to be even smaller. So we know that as between these two nodes, max is always going to choose the one with 3, not the value that's less than or equal to 2. Well, that means that if max is going to choose this node with a 3 and is never going to choose this node that's less than or equal to 2, there's no point in looking any farther for the children of this node because min is never going to, we're never going to reach that part. Either they're smaller than 2, in which case max isn't going to choose this node, or they're greater than 2, in which case min isn't going to choose them, and so this node will stay less than or equal to 2, and max is always better off picking this node. And therefore, we can prune the search right here and not expand. And that's an alpha cutoff. So here's another one. Let's say now we go to the third branch, and we find that the first depth first expansion here is going to be 14. Now, by the same reasoning as we had here, we know that the value of this node is going to be less than or equal to 14. Now, we might think, oh gosh, we should choose that, but wait a minute, we have to check and see what the other branches are. So let's look at it, and sure enough, the next one was a 5. So it's no longer less than or equal to 14, it's less than or equal to 5. And when we expand that out again, we get less than or equal, we get an exact value of 2. Now, in that case, because we have an exact value of 2, and this is always going to be less than or equal to 2, we know that the value of this node is not less than or equal to 3, it's exactly equal to 3. And that's alpha-beta pruning in action. So what are the properties of alpha-beta pruning? Well, it doesn't affect the final result because the way alpha-beta pruning works, it only prunes paths that are going to be fruitless to take. They won't lead to a solution, assuming rational play by min, that would be better than we can find with alpha-beta pruning. It turns out that choosing which moves to evaluate improves the effectiveness of the pruning. If you get the moves in perfect order, the time complexity is O of the branching factor to the maximum depth divided by 2, which doubles the solvable depth. In other words, you can look twice as far into the game. So somebody, an agent with alpha-beta pruning can do much, much better than an agent without alpha-beta pruning. And in fact, alpha-beta pruning is a simple example of the value of reasoning about which computations are relevant. In other words, the paths that are possible because min would choose them are relevant, and the paths that min won't choose are going to be irrelevant. And that's a form of reasoning about reasoning, or meta-reasoning. Now, the only problem, of course, is that even by doubling the solvable depth, we're still not going to be able to tackle chess because 35 to the 50 is still impossible. And with that cheerful note, I'll see you in class.